Alright, hello BC class. Today I'm going to be talking to you guys about geometric series. Alright, a geometric series is kind of like a geometric sequence in that you notice to go from one term to the next term every single time here, you are multiplying by 1/2, right? Just timesing 1/2 to get to the next term and the next term and the next term and so on, right? So we could actually write out this series, this infinite sum, right, using summation notation to say that if we were to let n be equal to 0 and go to infinity, this series would just be 1/2 raised to the nth power. So plugging in n equals 0 would give you the first term of 1, and then 2 would give you, 1 would be 1/2, and 2 would be 1/4, and so on, and it would add all of these terms together, right? This would be our geometric series. Now, in general, this geometric series, or pretty much any geometric series, is going to be similar, right? So this geometric series, in general, we're going to have our first term, whatever that might be, and then our second term is going to be a sub 0 times, now whatever this common ratio up here happens to be. For our example, our common ratio was 1/2, right? But here we're just going to call the common ratio r. So it's a sub 0 times r plus a sub 0 times r squared, and so on, infinitely. Now you might notice that the a sub 0's really aren't going to make a difference. We can write this sum as a sub 0 times r to the nth power, where n is going to be equal to 0 going to infinity for our infinite geometric sum. Or, if we really wanted to, you could factor the a sub 0's out of every single one of the term and just get a sub 0 times the sum n equals 0 to infinity r to the nth power, right? And this is still going to end up being our geometric series. Okay? So this sum, we're hoping, is going to converge and go somewhere, all right? Now, that's only going to happen, of course, if our terms get smaller and smaller and smaller. And I'll show this to you and prove this to you eventually. But what we need to talk about first is our partial sums, right? What is a partial sum of a geometric series? And then see what that partial sum might actually go to. All right? So let's consider a partial sum Let's call it the nth partial sum. All right, and so this nth partial sum is going to look like a sub 0 plus a sub 0 r plus a sub 0 r squared plus a sub 0 r cubed, all the way up to, now the nth partial sum is going to end at r to the n minus 1, right? That's actually going to have n terms to it, because if I had this as being n, you'd actually have n plus 1 term if you consider n being equal to 0, that capital exponent being equal to 0, right? So this here is our nth partial sum, and what I'd like to do is prove the formula for what this nth partial sum is going to be equal to. And if you watch my previous video where we actually proved that this geometric series here was equal to 2, this is going to be proven in much the same kind of way. So what we're going to do is we're going to multiply this nth partial sum. We're going to multiply both sides of the equation by r. And so on this side is going to be r times s, the nth partial sum. And over here, we're going to have a sub 0 r plus a sub 0 r squared, and so on until we get to a sub 0 r to the n minus 1 plus a sub 0 r to the capital N. Because when you multiply by r, that's going to increase that exponent by 1, so that's what your last term's going to be. And then what we're going to do here is we are going to subtract both sides of the equation from the top one. Because they're equal to each other, we can subtract them from both, right? So now on this side here, we're going to get 1 s sub n minus r times s sub n, right? And then on this side, the a sub 0 r is going to cancel. The a sub 0 r squareds are going to cancel. All these terms in between are going to cancel. And we're going to be left with a sub 0 plus a sub 0 r to the n. Okay, it might not look like much. We're trying to figure out what s sub n is, so I'm going to factor the s sub n out of here, yank it out front. And you know something? I'm going to factor the a sub 0's out on this side too, just for funsies. 1 plus r to the n. And now I'm going to divide over 1 minus r, and divide over 1 minus r, and that is going to give us our partial sum formula, which is kind of nice. Our partial sum formula is s sub n, the nth partial sum, is going to be equal to a sub 0, which represents our first term, and that's going to be 1 minus r to the nth all over 1 minus r. Okay? And there we go. That is our partial sum formula. So if you wanted to add together, like, let's say we had a series of a geometric series that we were using. Say the geometric series is, let's say negative 9 plus plus 3 minus 1 plus 1/3 minus 1/9, and so on. And let's say we wanted to keep doing this until we hit 1 over 84. Because the next one would be a plus 1 over 27, and then a minus 1 over 84. So this is a geometric sum where our first term, a sub 0, is equal to negative 9. Our common ratio of r is equal to negative 1/3, right? That is, you're dividing by 3 every single time, but it's alternating, so your ratio is going to be a negative, so that one term's positive, the next one's negative, and so on. Then we could find this partial sum, right, s sub n, where n in this case is equal to what? How many terms? 1, 2, 3, 4, 5, 6, 7. We've got 7 terms here? Yeah. So this is the 7th partial sum, right? And yeah, so it's going to be negative 9 times 1 minus negative 1/3 to the 7th all over 1 minus negative 1/3. Right? End up looking something like that. Should be able to calculate something like that. Negative 9, 1. This is going to be plus 7. That's going to be plus 1 over 2,187. All over, this is going to be 4/3 in the denominator. All right. And I think you could be able to figure out what that solution is going to end up being equal to for this partial sum formula. Okay? In general, the series up here, if I was to give this series a name, S, this series would be equal to, in a summation formula, of negative 9 times negative 1/3 to the nth power, and n starting at 0 and going up to 6. Right? Yes. I believe that would be 0. Yeah, because we're starting at 0, going to 6. That would be our 7th partial sum. Right? All right. So that is our partial sum formula. You can use it to calculate some of the partial sums that are in WebWork for our geometric series. Of course, an infinite geometric series just takes that partial sum formula and takes the limit as it goes to infinity, right? So an infinite geometric series is going to take a sum, which is, of course, a sub 0 r to the n going from 0 to infinity. Right? We turn this into an nth partial sum, which is the formula we just came up with. So that's n going there, a sub 0 r to the nth power, which we now know equals a sub 0, 1 minus r to the n all over 1 minus r. And then we need to take the limit of this nth partial sum as n goes to infinity. And we'd like to know if that converges or what have you. So really, we're taking the limit as n goes to infinity of this new formula that we created. A sub 0, 1 minus r to the nth power all over 1 minus r. And really, all of this is going to depend upon what happens here. Because we're going to have, kind of 3 cases with this a sub 0 r going to infinity, right? So if the best case, r is in between 1 and 0, so it's some kind of fraction, doesn't matter whether it's positive or negative or not, it's going to be fine. This whole thing is going to converge. Because if r is a fraction, that's going to end up going to 0, and we're just going to get a sub 0 over 1 minus r. If your common ratio is 1, then that just means you're adding the same thing on top of the same thing every single term. You're not going to go anywhere, because no matter what a sub 0 would happen to be, you would just be constantly getting a sub 0 plus a sub 0 plus a sub 0. And really the only way, there's going to be a theorem about this, the only way that a series is not, or I'm sorry, one of the few ways that you can tell right away that a series is not going to converge is if that common ratio, or if any of the terms, right, if the terms don't decrease and get closer to 0. Your terms have to get closer to 0. If they don't get closer to 0, then it's not even possible for your series to converge. If you keep adding 1 on top of itself every single time, you're just going to be infinite. You keep adding more terms, you're just going to keep getting bigger numbers. But if that ratio is a fraction for a geometric series, meaning your terms keep getting smaller and smaller and smaller because you're multiplying by a smaller fraction, a fraction smaller than 1 every single time, yeah, we have a possibility to converge here. And with this partial sum formula, this geometric series partial sum, we will converge, and this will be what we converge to. All right? If r is greater than or equal to 1, this is going to diverge. All right? That is, your sum is not going to equal a darn thing. All right? Truly, I like to say that, if you're the simplified formula for the convergence of a geometric series, that is with your common ratio being less than 1 but greater than 0, we're always going to get the sum of that series to be equal to the first term divided by 1 minus the common ratio r. That is what your infinite sum is going to be equal to. First term divided by 1 minus r. Okay? And so if we go back to that original example of 1 plus 1/2 plus 1/4 plus 1/8 and so on, that is going to be equal to 1 is your first term divided by 1 minus 1/2, which does equal 2. All right? And so that's it. Okay, if you're trying to find a partial sum only going out 50 terms or 100 terms, we're going to use this partial sum formula. All right? If you're going out an infinite number of terms and you know your ratio is between 0 and 1, this is the formula we're going to use. First term divided by 1 minus your common ratio. All right, so I hope this helps with geometric series. I'll be posting some work for you guys to try. And yeah, so good luck. Email me, stop by anytime if you have any questions on this. All right, thanks.